This is an introduction to the Donnie Watts Generator. Donnie Watts has designed a simple generator which is capable of providing enough electrical power to meet the needs of a typical household. The design is based on well-known principles, and this engine runs cold and is simple enough for many people to be able to build one. The output power increases with the rotor diameter and with the rate of spin. And so in order to stop the device accelerating until it destroys itself, an inflow valve to limit the water entering the rotating cylinder or other effective means of speed control is an important requirement. What needs to be understood very clearly is that this is an exponential power engine. The output power is proportional to the square of the rotation speed. So if you double the revolution speed, you then quadruple the output power. Also, the output power is proportional to the square of the rotor diameter. So if you double the diameter, then that quadruples the output power. So if you double the rotor cylinder diameter and you double the rotation speed, the output power goes up by a factor of 16 times. The basic coefficient of performance for the design is 4. That means that the output power is always at least 4 times greater than the input power. This information comes from 2 separate patents. The first was in 1989 and shows a generator which could be built by most people. The second was 3 years later and is much more complicated, suggesting mechanical methods of controlling the rotor speed. I suspect that few people would be able to build the later design. Both patents are shown at the end of this document. However, I will concentrate on the simple version so that you have a chance of building one for yourself. Donnie Watts says that initially it is necessary to start the device with the water pump, but when the rotation reaches 60 revs per minute, the device no longer needs the water pump, although the water pump can be left running if desired. At 60 RPM, the pressure inside the rotor drum reaches the point where the suction caused by the water passing through the rotor jets creates sufficient suction to maintain the operation. But remember that this is a positive feedback system, with an increase in speed causing an increase in power, an increase in water flow, an increase in speed of rotation, and so on. And consequently the engine will run away self-powered. And if you're not ready for that with a throttle on the rate of water flow into the cylinder, then the engine is perfectly liable to accelerate to the point where internal pressure damages the engine, probably causing the rotor drum to leak. However, it occurs to me that an alternative way of starting the generator would be to spin the rotor with an electric motor temporarily attached to the output shaft of the device, or possibly even with a manual starting handle like early cars used. Anyway, in broad outline, Donnie originally showed the design like this. You have a hollow cylinder which is 48 inches in diameter, 6 inches thick, and has 16 jets angled at 25 to 30 degrees to the cylinder tangent. There's a special coupling, one side of which is stationary, the other side of which rotates, feeding a fluid into the drum via the pressure applied by a pump, and with a valve in the line so that you can shut it down or choke it off to a lower speed if that becomes necessary. The output shaft through pulleys drives an AC generator or alternator. The circular rotor has water or whatever fluid you want to use pumped into it by the pump. Most generators require to be spun at 3000 revs per minute or slightly faster. That speed can be achieved by the belt gearing between the output shaft and the generator's input shaft. That linkage there. A generator of that general type could look like this particular one here, which is a 5 kilowatt alternator, which in 2018 cost £325 in the UK. However, the output power of this design is said to be further increased by the inclusion of thrust baffles on the inside of the housing. The idea is to have jets of water strike a fixed surface at right angles to the jet and as close to the jet nozzle as possible. However, the later patent points out that while the jets always apply their thrust to the rotor drum, no matter what speed the drum is rotating, once the drum gets up to speed, the fluid coming out of the jets is nearly stationary relative to the sump, and so these baffle plates would only be helpful when starting from stationary. Let me stress that this device is effectively a fuel-less engine with a substantial power output. It can be built in various configurations. This is one build here where it's set up vertically. The 1992 patent is shown at the end of the document, but due to the difficulty of constructing that version, I will stay with the original construction, which has the axle shaft horizontal, and so the axle and drum weight do not apply a sideways load on the bearings. Donnie Watts shows a 48-inch drum, which is 1220 millimeters diameter rotor drum. Inexperienced constructors almost always decide that instead of constructing what is shown, that they will improve the working design by changing it to their own ideas. That almost never works, and what they are testing is their own design and not the design which they're trying to replicate. And then they end up going online and saying, "Oh, this design doesn't work. I built it and it doesn't work," ignoring the fact that they never ever built it the way it was designed. But anyway. For example, the pipe feeding water to the drum is specified as being 3-inch or 75 millimeters in diameter. An inexperienced constructor chooses to build a smaller diameter drum and so decides to reduce the supply pipe diameter to 1 inch or 25 millimeters. No, no, no. Definitely not. This is a very, very important component which must not be changed. Just because you decide to use a smaller drum does not also scale down friction nor the difficulty in pushing water through a pipe. A 75 millimeter diameter pipe has a cross-sectional area of 4,417 square millimeters, while a 25 millimeter diameter pipe has a cross-sectional area of 490 square millimeters, and that's only 11% of the 75 millimeter diameter pipe. In other words, to match the 75 millimeter diameter pipe's capability, you would need 10 25 millimeter diameter pipes to carry the same flow, because the smaller pipes have greater friction. Donnie also stresses that the inlet pipe must have nearly twice the cross-sectional area as compared to that of all the jets combined. The later patent appears to raise that factor to 8 times the sum of the jet openings. If you find this hard to believe, then take a 1 meter length of ordinary garden hose pipe and try to blow air through it. Although the pipe has a diameter of 12 millimeters or so, you will see how hard it is to blow air through it. If you build a generator with a 1-inch diameter pipe between the pump and the drum, then you probably will not get the rotor over 300 revs per minute, which is 1 per second, as that lower sized pipe is the equivalent of throttling the pump down to 10% of its input capability. The smaller you make a Donnie Watts generator, the more accurate your construction has to be. For that reason, I strongly recommend that to make the drum you should use at least 1 meter in diameter. An American developer, Rick Evans, has come up with a way to avoid the need for a special supply hose coupling, and his method looks like this. The water in the sump is drawn up through the pump, through the valve, and into a container which encloses both the rotating pipe axle of the drum and the bearing which supports the drum. This is a very useful addition because it's difficult to get rotating pipe coupling of that sort of size and ability. It's a very clever solution. There are many different ways to construct a Donnie Watts generator. The method shown here is merely a convenient method of construction using 3mm, which is 1/8 inch, thick mild steel, and a welder. The diameter of the rotating drum can be whatever you choose, but the output power increases with the square of the diameter. So if you double the diameter, the output power becomes 4 times greater. This example is going to be based on a 1 meter diameter disc. You start by cutting out 2 discs, one with a 3-inch diameter central hole and one with a central hole of the size needed for the axle of your pulley wheel, which attaches to the alternator. Then, having cut out the 2 circles of steel, you weld on 8 rectangular pieces of steel which are 144mm wide. You weld them to the disc which has the smaller hole. So there's your disc, and there are the 1, 2, 3, 4, 5, 6, 7, 8 pieces of rectangular steel which are welded to your circular drum. Those form channels for the water or other fluids such as transmission fluid as it passes through the drum when the generator is operating. There must be at least 50mm or 2 inches clear between these plates and the edge of the disc. That's this space here between the end of the plates and the end of the discs. That's to allow water to flow easily past the plates around the rim of the drum itself. The 144mm depth of the plates allows clearance for the second disc to be welded in place to form a drum. Seen from the side, it looks like this. Then the outer rim of the drum will be welded in place. If you have never built anything in steel, let me assure you that it's not at all a difficult thing to do. And yes, I have built in steel, starting as a total beginner. However, while mild steel is easy to work and weld, stainless steel is much more difficult, so avoid stainless steel. Steel pieces are cut and shaped using an angle grinder, like this. And while the picture shows a handle sticking out of the side of the grinder so that you can use 2 hands, it's generally more convenient to remove the handle and just hold the grinder in 1 hand, as it's not heavy. When working steel, wear a pair of rigger gloves, which are strong reinforced gloves and will protect your hands from sharp steel edges, and always wear eye protection. If you're going to be drilling steel, then a mains powered drill is needed, as battery powered drills are just not up to the job, unless it's for just one single hole. When drilling steel, it is helpful to have an additional hand grip attached to it. With this particular drill here, the circular projection here on the drill itself allows you to clamp a hand grip around that, and the hand grip can be set at any angle. Steel pieces are joined together by welding. Some welders are quite cheap. Most types can be hired for a day or half a day. It's also possible to shape the pieces and have a local steel fabrication workshop weld them together for you. And making a good welded joint only takes a second or two. The really vital thing is never look at a weld being made unless you're wearing a welding visor or welding goggles, as you can damage your eyesight by looking at a welding arc without protection. If you decide to buy a welder, then be sure to get one which will run on your house main supply. Otherwise you have to upgrade your house wiring to carry the higher current. This particular welder will be suitable, and at the start of 2016 it cost only £60, including tax, which is about €82 or $90. With this so-called stick welder, the silver clamp on the right is attached to the metal to be welded, and a 2.3mm diameter coated welding rod placed in the black clamp. The stick is then applied to the welding area, and the coating on the welding rod becomes a gas cloud, shielding the hot metal from the oxygen in the air. When the weld is cooled down, there may be a layer of oxide on the outside of the joint, so the back of the wire brush can be used as a hammer to break up the layer, and the wire brush itself used to scrub the joint clean. However, the most important item of equipment for anybody doing welding work is a protective helmet. There are many different designs and widely varying costs. Many professional welders choose one of the cheapest types, which looks like this. This type has a clear glass screen and a hinged safety filter. Professionals adjust the hinge tension so that the filter can only just stay in its raised position. The welder then positions the joint pieces in their exactly correct position while looking through the plain glass, and when ready to start the weld, he just nods his head, which makes the filter drop into place, and the weld is started. Once the weld is started, you can see clearly through the filter. Never ever try welding without proper eye protection. Welding is easy to learn, and it's a brilliant method of construction, but it has one major problem. When a joint is made, the two pieces of steel melt and merge together. This can happen in a tenth of a second. Don't put your finger on the joint to see if it is still hot. If it is, then you get a painful burn, and that should remind you not to do that again. That heat is a problem because when steel gets hot, it expands, and when it cools down, it contracts. That means if you were to set up a piece of steel at exactly right angles and weld the pieces together, then as soon as the joint cools down, it contracts and pulls the joint out of alignment. So what was vertical is no longer vertical. Please don't imagine that you can just push the vertical piece back into position, as that isn't going to happen, because the joint is instantly very, very strong. Instead, you use two quick welds of equal size, with the second weld being 180 degrees opposite the first one. So you do one weld on this side and immediately one weld on the other side. Then when the welds cool down, the pulls oppose each other and the vertical piece stays vertical. Metal can be cut quite readily using a cutting blade in your angle grinder, but be sure to install the blade so that it rotates in the direction shown by the arrow on the blade. The blade is likely to look something like that. When cutting or grinding, always wear protective goggles to make sure that you don't get a metal fragment in your eye. Eyes are not readily replaceable. If you do get a small steel fragment in your eye, remember that steel is highly magnetic, and so a magnet may help in getting the fragment out with a minimum of damage. However, it's much easier to wear goggles and not have the problem in the first place. The Donnie Watts drum spins on an axle, and so it needs a bearing on the axle pipe which supports it. The flow of liquid through the drum will be substantial, and so Donnie recommends a 75mm or 3-inch diameter pipe as the axle. That may sound excessive, but the reality is that it's quite difficult to force liquid through a pipe, as it's much greater back pressure than you would expect. So use a 75mm diameter pipe. The next step is to attach the outside strip to complete the basic drum. If you are great at bending 3mm thick steel, then do that, but most constructors will find it much easier to weld, say, 32 strips 150mm tall around the outside of the drum. That makes it easier to attach nozzles to complete the drum at a later stage. Here we will assume that the drum has been built by a professional steel fabrication shop, which can bend 3mm thick steel to the required curvature, that is, to the diameter of the drum. The outer edge of the drum is welded all along its length. The weld needs to be airtight, but please understand that due to heat stress, long welds need to be done in short lengths of, say, 25mm in length or less, preferably less, and allowed to cool before the next weld is made. The technique is to make this series of short welds spread out along the length of the long weld, and when those short welds have cooled down, then they're each extended for another 25mm. Slow and careful construction is easily the best method. We now need to attach nozzles through the outer wall of the drum. A hole needs to be drilled through the outer wall for each nozzle. As with all holes drilled through steel, the hole is drilled at right angles to the steel, that is, perpendicular. I'm not saying that you can't drill a hole at an angle, but it is very, very difficult to do without breaking the drill bit, and it's very difficult to hold the drill steady enough to get the hole started. We want to have the jet of liquid leave the nozzles at 25 degrees to the face of the steel, so that it doesn't hit the next nozzle down the length of the circumference. We also want the jet orifice to be 1.5 millimeters in diameter, so we need to construct jets from steel pipe with that internal diameter, insert them through the outer wall of the drum, and weld them in place. How many jets? I would suggest 16, but the number is not critical. It is said that the jets of water are more effective if they strike a nearby surface, so we may choose to attach a series of baffle plates to the outer housing. How many baffle plates? I would suggest 16, but these baffle plates are only effective when starting a stationary rotor, and so they can definitely be omitted if you prefer. The diagram of the sump enclosure drawn by Donnie shows angled top edges, but it's probably easier just to use square plates, as there's less cutting and welding if you do it that way. Donnie suggests that the housing plates need to be 300mm wider than your drum and have 150mm clear above it, and 150 plus 200mm, which is 350mm, clear below it, as the bottom of the housing acts as a sump for the liquid which passes through the jets. So 6-inch gap at the top, 6-inch gap on one side, 6-inch gap on the other side, and 14-inch gap at the bottom. That is, if you work in inches. Now, you need to insert a ball bearing or roller bearing into the back plate of the sump enclosure, which will house the drum. But make sure that the drum, when it's rotating, clears all of the nozzles or baffles welded to the drum. There's no need for additional housing. There's a pump needed to get the system started, and that can be mounted on the outside of the drum, as the drum housing rather, as can the generator. The supporting axle pipe spins with the drum, driving the alternator generator, which provides the required mains voltage AC output, and that'll be mounted on the outside of the housing as well. This overall arrangement produces a device which is much taller than it's wide. So a stability plate, which is here along the bottom, is welded to give it stability in the left-right direction as shown in this particular diagram. While the axle shaft can be made of two parts welded together and welded to the drum, I suggest that it's more practical to weld the incoming 3-inch diameter pipe to the drum, and then choosing a solid bar of steel whose diameter matches the side needed for your chosen pulley wheel. That bar is welded to the other side of the drum as shown above, so your pipe is welded on one side and your solid bar shaft is welded on the other side. Both of course have to be exactly aligned and exactly square to the drum, being perpendicular. That gives you the drive to the alternator. The generator is said to be started off and operated by a pump, and so either access to mains supply voltage or alternatively access to a battery and inverter is essential. Once the generator is running, the pump can be powered by the generator. It is stated that when the speed of rotation passes 1 drum revolution per second, that the liquid passing through the jets causes enough vacuum inside the drum that the pump can be powered down. But it is also possible to leave the pump running all the time if you want. People sometimes have difficulty in understanding the pressures involved. The drum, which revolves, is the only place that there is pressure when the generator is operating. The outer case has only two main functions, namely to support the drum so that it can rotate, and the other function is to act as a sump, collecting the liquid that has passed through the drum and making it ready to go back through the pump and valve back into the drum to continue the operation. Concerns have been expressed that the pump undergoes unnecessary wear when the generator is running and the pump is no longer needed. So if you like, the pump can have a bypass which is valve controlled like this. So the water in the sump goes out through a T connector, through a 3-inch wide pipe, into the area that feeds the rotating pipe, which is part of the drum axle. The pump then can be switched off and the valve here closed permanently if you wish. That allows you to actually take the pump away if you want, but anyway, it's not something that you need concern yourself with. You can stop the pump operating all the time if you want by doing that. That does require some additional piping and a T-junction for the pipe bypass, but it allows the pump to be switched off when not needed. Let me stress again that this is an exponential positive feedback design which will keep accelerating until the bearings fail or the pressure inside the drum causes some form of rupture which will starve the jets of liquid, or the generator might fail due to excessive speed. While this may seem like irrelevant theory, I assure you that it isn't. You have this generator running and powering your house. The weather is hot. You have an air conditioning unit keeping your house cool. The air conditioner draws a lot of current, but then the thermostat switches the air conditioning off because your house is cool enough. This is a problem. The current draw from the generator goes down by a major amount. This makes the generator shaft much easier to spin, but the drive power from the Donnie Watts unit is now much higher than is needed. This is not helpful, and the system is now unbalanced, and the drum will speed up, spinning the generator shaft faster than it should. If you're standing there and adjust the control valve accordingly, then everything goes back to normal. But the point is that a generator of this type is fine for a fixed load, but you need to pay attention to what the electrical load is if it changes suddenly. You could build an automatic valve adjustment to make an automatic speed control, or install one or more pressure relief valves. The later patent is mainly about automatic speed control of the drum. As some people find this generator hard to understand, let me explain it in broad outline. The device is essentially a motor. It is a motor which is a spinning drum inside a support housing, which acts also as a sump. This is a self-powering motor, and the faster it goes, the higher the power level which it generates. As that is a positive feedback system, the motor will keep accelerating and gaining power until it exceeds the strength of the materials used to construct it, and so it breaks the drum open. In order to prevent that happening, an adjustable valve, which is the equivalent of a large tap or fire hydrant valve, can be placed in the pipe which feeds the liquid into the spinning drum. That valve acts as a manual speed control for the motor. In order to produce useful work, this motor design is used to power a separate electricity generator using 2 pulley wheels and an alternator, making the design a motor generator design. It's not easy to spin the alternator when it is supplying substantial amounts of electricity to washing machines, tumble dryers, air conditioners, heaters, stoves, TVs or whatever. And so the alternator acts as a brake, slowing the motor down. That doesn't matter, as the speed control valve can be opened a bit to get the speed back up to what it should be. It is important to spin the shaft of the alternator at the speed it's designed for. Spin it too slowly and it will produce a voltage which is less than mains voltage, and a frequency which is less than that of the mains. Spin it too fast and the generator will produce a voltage which is higher than mains voltage, and a frequency which is greater than the mains frequency. Typical design speeds for spinning the shaft of an alternator range from 1800 revs per minute, that's 30 revs per second, and 3000 revs per minute, which is 50 revs per second. Alternators are designed to produce either 110 volts at 60 cycles per second for American equipment, or 220 volts at 50 cycles per second for everybody else. This is fine if the electrical load is constant and the speed valve is adjusted correctly, but we have a problem if the electrical load drops suddenly. Because the electrical current is dropped, the shaft of the alternator becomes much easier to spin, and so it acts far less of a brake. And because the valve setting is unchanged, the motor speeds up. This is not a problem if there is a human standing beside the generator ready to adjust the valve setting accordingly. Unfortunately, that's not convenient, and worse still, many electrical appliances switch themselves on and off on a regular basis, and the basic Donnie Watts design is not able to cope with that. So it would be very convenient if we were to make the Donnie Watts motor adjust its own control valve. Let's see if we can come up with a simple system for doing that. Commercial valves are generally not suitable for this, as they are either fully on or fully off, and they're not electrically adjustable to give intermediate settings. Also, they tend to be far too small a diameter to interest us, but we can indeed use them if we wish, but more about that later. For home builders, it would probably be easier to use a 16-sided shape rather than a circular disc. Apart from all being straight side cuts, there is the advantage that the plates which form the circumference of the drum, can become drilling points for a system which is more simple than using pipe nozzles. Where plates meet at an angle like this and are joined together, you can drill a simple hole at the correct angle through the join between the plates. It's very simple to do, and you can use an angled template to guide the drill in at exactly the right angle. It's straightforward to do that, and it's quite possible to do it. Now, to make the first drum side, we start with a square piece of 3mm thick mild steel, which is 1 meter by 1 meter in size, or if you prefer 1000 millimeters by 1000 millimeters. You draw diagonals from the corners to establish where the center of the square is, and you then draw vertical and horizontal lines to that point. You measure 500 millimeters from the center point out along each diagonal and mark each of these points. Then you connect all of those points together to make an even octagon. Next, you mark the central points of each of the 8 sloping lines and draw a line from the center point through each of these new points. That gives you 16 lines coming out from the center at equally spaced angles. Mark 500 millimeters from the central point out along each of these new lines, and then connect those points to give you your 16-sided drum piece. When you cut along that, you end up then with 16-sided, completely even side of the drum. When you've got that first side, you clamp it to another piece of 3mm thick mild steel and mark carefully around it, get the shape and size of the second side of the drum. Cut around this new side and draw some diagonals on it to establish the center point. One of these two drum plates needs to have a 3-inch, that's 75mm, intake pipe installed as an axle. You could get a local steel fabrication shop to drill the hole for you. Alternatively, you could mark the exact position and size and drill a ring of small holes around the circumference, and then with a small cutting blade in the angle grinder cut between the holes, and then using a grinding disc in a power drill smooth out the unevenness between the holes to give a reasonable quality hole accurately positioned. Remember to use goggles for both cutting and smoothing. Another way would be to rent a plasma cutter and air compressor for a morning and use that to cut an exact hole. Having got the exactly positioned hole in the drum side plate, the pipe needs to be welded in place. For doing that, these magnetic angles are enormously helpful. They're 4 inches along each side, or 100 millimeters along each side, and they are low cost, and they grip steel and the steel pipe very strongly, and they make a perfect 90-degree angle. Using 4 of those magnetic clamps, you can hold the pipe securely and accurately. Remember that the moment a weld is made to one side of the drum plate, the other side of the drum plate needs to be welded immediately, and both allowed to cool as slowly as possible to avoid heat shrinkage, pulling the pipe out of its alignment with the drum plate. Remember that the drum plate will be hot enough to burn you, even if the weld only took a split second to make, so take care. In other words, if the pipe is vertical, then almost simultaneous welds need to be made on top of the drum plate and on the underside of the drum plate. The thicker the steel, the easier it is to weld without problems, and so welding the pipe is straightforward. It takes a great deal of skill to weld steel sheet of 1mm thickness without tearing a hole in the sheet, but thankfully that's not something which you need to bother with, because you don't have to do it. Having tack welded the pipe carefully and quickly on both sides, using welds of only 6mm or so long, and having waited for those welds to cool down fully, make 2 additional tack welds at 180 degrees around from the first 2, and then 2 more pairs, so that you have a weld every 90 degrees around the pipe. Then wendling all around the pipe is completed only in very short lengths in opposing pairs, and letting the welds cool before making the next weld. A cheap workmate bench like this makes a good support for this work, and it allows the pipe to be gripped securely while the drum plate is resting horizontally on the bench. If you feel that an open 3-inch diameter pipe is not sufficient to get the liquid into the drum, then make as many openings or drill holes or angle grinder slits as you can consider necessary in the drum pipe on the inside of the drum. So in other words, the pipe inside the drum can have lots of holes or cuts in it. Mild steel 3mm thick can be supplied in 150mm wide strips. They're 8 feet long. One of those would reduce the amount of steel cutting needed to complete the drum, as it's needed for the internal channels and for the circumference wall of the drum. The inside walls need 6mm taken off them if you're going to do that. As the drum diameter is 1000mm and 150mm is left around the center and 50mm is left at each side, the 8 internal walls need to be only 500 minus 75 minus 50 equaling 375mm, which is 14.76 inches long. The 150mm clearance in the center of the disc does not need to be exact, and so cutting 370mm from your 150mm strip will do nicely for all 8 walls. As we want to use the width of the 150mm strip to make the 16 circumferential strips, measure the exact width of the strip supplied to confirm that it's 150mm wide. I have never been supplied a strip which was not accurately 150mm wide, but check carefully to make sure that your strip is exactly 150mm wide, and adjust the measurement slightly if it isn't. That's the measurements of the internal walls I'm talking about. Ideally, the strip is exactly 150mm wide, and so the inner walls will be 144mm wide and 370mm long. So 6mm needs to be removed from each of those 8 internal walls, unless you choose to cut them directly from sheet. Using the magnetic clamps to hold each plate vertical when positioning and tack welding it, you tack weld all of the plates 1, 2, 3, 4, 5, 6, 7, 8 on the inside of one of the plates. Complete the welding of these 8 plates, remembering to take it slowly, remembering to always use simultaneously opposing welds and allowing each weld to cool naturally. The next step is to attach the second side of the drum. The really important thing here is to align the second side exactly, and the magnetic angles are useful for doing that. Measure the straight edges which form the circumference to your drum and cut 2 150mm strips to that exact length. It's probably better to do the marking of the steel strip directly against the rotor drum rather than relying on measurement. You can make a mistake in measurement. You can't make a mistake when you put the piece up against the drum and mark it off. You go around the whole drum once you have the second side aligned to where you think it should be, and confirm that the 2 drums match exactly. Be very sure that all flat edges match exactly, and when you make your first tack weld on the second drum side, that is it, and you've no realistic chance to change the positioning. Once you're satisfied that the second drum is positioned exactly right, make 2 opposing tack welds on the upper second side of the drum, like this. One there, one here. These welds are made upwards, so be sure that you're wearing good strong gloves, as getting molten metal on bare skin is not a pleasant experience. Then you make 2 more opposing tack welds, like this one here and this one here. You can then turn the drum over so that the following welding is downwards, and you're not liable to get hot metal coming at your hands. There's room to weld inside the drum, as the pieces forming the channel walls are only 360 millimeters long, and there's 144 millimeters of clearance between the drum sides. These 8 short pieces hold the drum sides securely and give the drum major strength. Strictly speaking, the above diagram should show 16-sided discs rather than circles. We come now to attaching strips to the side of the drum to form the outer drum wall. Remove the magnets and alignment side strips and turn the drum sideways and clamp it in the workmate so that the drum edge is facing upwards, and so it's easy to work with. The vertical outer wall of the drum is made up of 16 strips of steel, each 150 millimeters wide. Each strip will be about 196 millimeters long, but that length is marked on the strip directly against the straight side of the drum disc. You start by welding these narrower strips as the vertical walls. Take 2 edging pieces already cut and weld them to the drum in opposite positions around the drum. You do one at one side and then the other one at the other side. The welds can be made inside the drum if you want. 2 more circumference pieces are then measured carefully, cut and welded like this, one opposing the other. So you then have 4 at 190-degree intervals around your disc. Then you do 4 more, spacing them out, and this is where it becomes interesting. The final plates need to be measured very accurately, and they will be welded in place like this, so that there's a V-notch between each plate. The V-notch between the plates is very important, as it's where the nozzle jets will be drilled. You have the sides of the drum and 2 plates being welded to it with a V-notch between them. So you drill a hole through the plates in the middle of the 2 plates in the joint between them. You drill it at the correct angle that's chosen, and that's the way that you create the jets without any extra welding. It may be necessary to lower the next circumference plate just opposite the jet exit using a grounding tool so that it doesn't interfere with the jet or liquid leaving the drum, and that would be this point here, but it generally speaking is not likely to be necessary. So after all that effort, you now have a strong and secure drum, but it only has a 3-inch diameter inlet pipe attached, and we need the axle support bar on the other side of the drum. What diameter should that bar be? I don't know, because it needs to have a pulley mounted on it. I would expect it to be about 25 millimeters or 1 inch in diameter, but you need to search suppliers for pulleys and buy 2, one for the drum and one to match the drive shaft diameter of your alternator. Obviously, the 2 pulleys need to work with the same drive belt. Ideally, the drum pulley should be 2 or 3 times the diameter of the alternator pulley. In fact, any ratio up to say 5 times would be good, as the working output of the alternator will be reached at lower drum revolutions, and that would give smoother running if the drum construction is not perfect. So we have identified what shaft diameter is needed for the drum output, and we've purchased a mild steel bar of that diameter. The center point of the second drum side is marked. If you have cleverly welded it on the inside of the drum, then draw diagonals to get the center point on the outside. Check it by clamping the 3-inch pipe in the workmate, placing the drum inlet pipe in it, and spinning the drum. The center point should appear stationary when the drum spins. Holding a felt tip pen stationary, mark a small circle by touching the drum close to the center, say a circle of about 30 millimeters in diameter. This is where the pulley bar needs to be welded. Using the 4 magnetic clamps to position the bar in the middle of the circle, with the clamps at 90-degree angles to each other, spin the drum again to make sure that the bar does not appear to move. If it does appear to move, then correct the position until the bar seems motionless. Then tack weld between the magnets. Unfortunately, heat destroys magnets, and so welding so close to the magnets might destroy them. Thankfully, they're very cheap to replace. Now that we have completed the drum, we need to make the support housing, which also acts as a sump for the liquid, which is passed through the drum. In passing, while the Clem engine uses cooking oil as liquid because the Clem engine generates a good deal of heat, some people suggest using transmission fluid in the Donnie Watts design, primarily so that it lubricates everything which it passes through. The container which acts as a sump can be a rectangular box. It is specified that there should be 150 millimeter clearance on both sides of the drum. So the sizes for the pieces are shown here. The front and back are 1.5 meters tall and 1300 millimeters wide. The sides are 300 millimeters wide and 1.5 meters tall. The top is 1300 millimeters wide, 300 millimeters deep. The base is 2000 millimeters or 2 meters long and 600 millimeters wide. This gives you a good deal of stability in the box. The front and back have the front has a 3-inch diameter hole drilled in it. The back has a hole drilled in it, if you wish, which is the size of the bar that you use for your alternator drive. Strictly speaking, that isn't actually correct. The hole size for the 3-inch pipe is the 3-inch pipe plus the size of the bearing that holds it. The same goes for the hole on the back. The hole size is the size needed to allow the bearing of the solid shaft to pass through the hole. The bearings can be tack welded to the actual plate itself. The next step is to construct baffle plates to catch the jets of liquid coming out of the nozzles of the drum, if you decide to use them. Personally, I think they're probably a waste of time, but you can put them in if you wish. The hole is created in the front panel and the bearing is attached. The bearing will be the best 75 millimeter diameter bearing, which will fit your intake pipe and mount securely to the front panel. You can have it bolted or you can tack weld it. With the bearing fitted in place, the front panel on the workmate is used to support the drum face, and it can be clamped in place. This gives you a flat horizontal surface with the drum in its exact position. Clamp the drum in place so it can't move, and if you want baffle plates, then use one of the magnetic clamps to position each piece and mark the position of the first baffle. With the drum fixed in place, mark the position of the matching 15 other baffle plates. Unclamp and remove the drum so that there's a clear unencumbered work area. Using magnetic clamp, positioning one baffle plate and tack weld it in position, the tack weld on the drum side and an immediate matching tack weld on the side away from the drum. Remember that we need matching welds to stop the cooling weld pulling the baffle plate away from the vertical. Next, you put the drum back and give it a spin to make sure that the drum clears all of the baffle plates. I seriously doubt the spacing specified for the housing. The liquid squirts through the drum nozzles and hits the baffle plates, but then where does it go? It has lost its momentum and it will just fall under gravity. Some will fall on the drum, which will hurl it off to the wall where it will fall down into the sump. Part will fall clear of the drum and will fall down the side of the housing. So why the gap? 75mm should easily be enough to allow that to happen, no matter what the drum diameter is. 5mm of space outside the baffles should actually be quite enough. The physical size and shape of the pump is not important. It's located outside the sump housing. I've been asked what is the minimum pump size, but I don't know. The most I can say is that Donnie Watts specified a 500-watt pump for his 4-foot diameter drum, but I feel that a more powerful pump would be helpful. Please understand, I have never built or even seen a Donnie Watts generator. I believe that it will work exactly as specified, especially since the very similar Clem motor worked well, but I can't guarantee that it will. In passing, if the arrangement where there is a pump bypass pipe and valve, then one pump could be used to start a whole row of Donnie Watts generators by disconnecting the pump from each end as soon as it's running properly. But anyway, there need to be valves to stop the liquid spilling out if the pump is removed, but we can ignore that. Purely on and off valves are not expensive, even in 3-inch diameter. This is a typical one which is on offer on eBay, 3-inch size, and they're looking for $30 for it, and now that can be used as your emergency controlled stop valve on the inlet pipe to the drum. It appears that the valve is either fully on or fully off. There are valves which claim to be fully adjustable under electronic control, but nothing suitable has been found. So for the moment assume that the generator will be run under constant load, and just construct the box surrounding the drum intake pipe as 300 by 300 by 150mm in size, with a removable 300 by 300mm side sealed with a plastic or rubber gasket. If you feel that a generator which is restricted to a fixed load is really not at all that useful, then think again. Consider using it to power Nelma Grimes' water supply system. The US patent 2996897 of the 22nd of August 1961 is more than 50 years old, and it describes a system which can produce drinking quality pure water. It is effectively an outdoor refrigerator. A series of cone-shaped metal panels are stacked together vertically to save space. Each cone has pipes inside it which pass the cooling fluid through the cones, ensuring that they're always at low temperature. In the same way that a cold drink gets water droplets on the outside of the glass, the cones get water droplets forming on them all the time. A wiper arm, like a windscreen wiper on a car, then brushes those droplets off, with the wiper arm rotating around the cones continuously rather than backwards and forwards as a car wiper blade does. This produces a continuous stream of fresh water coming off the cones. Unless there's some good reason why not to, the cones are mounted in a raised position so that gravity can be used to direct the water flow to where it needs to end up. Cones are used as they have a greater surface area than a flat plate of the same diameter, and the downward slope of the cone helps the water droplets flow off the cone surfaces. This is the top view. There's this outer circular housing, but the cones themselves here have got a wiper arm that goes along the top and the bottom, and inside each of these sloping cone surfaces there is a series of, or rather one continuous cooling pipe which has cooling fluid pumped through it. There are also slots cut in each cone to let air pass through to the cones below it. It is a very simple, straightforward and very effective design which produces good quality water in considerable quantities directly from the air. And a system like that can even work in Death Valley, where it's extremely hot and dry. One of these Grimes systems produces enough water to support a ranch in Texas during a drought, and it could be powered indefinitely by a Donnie Watts generator. Think of the effect one would have on a village which has only access to polluted water, especially if you don't know the technology for colloidal silver. As it is probably not necessary to produce drinking water all the time, the generator could power electrical cooking in areas where firewood is getting scarce, charge mobile phones, power TVs, power fans, refrigerators and so on. The inside of the sump housing is not pressurized, and it is a very wet area. We don't want any oil leaking out through the drive shaft bearing, so we provide a steel umbrella to cover it. The side of the sump wall can have a protective steel cover, making sure that it stays as dry as possible. To make one of those, you cut 2 triangles in steel and attach them to the side wall to protect the bearing. Some people may prefer to use commercially constructed components, so let's see if we can come up with a low-cost automatic flow control system. For the system to be automatic, I suggest that we could use electrically operated valves, which can then be governed by a simple control unit. The vast majority of such low-cost valves are only half an inch in diameter and are made for central heating systems, and they're closed unless they're fed with power to open them. I would suggest the following valve. This plastic 1-inch diameter valve costs about £8. We can get variable control from these fixed valves by using a whole row of them to restrict flow. For this we use a second liquid fill box like this. We have a row of say 10 valves, 1-inch diameter valves, connecting the 2 boxes together, but we can control which of those valves is open and which is closed. The row of 10 valves allows 10 different flow settings when the valves are switched on or off by the control circuit, and there's the added advantage that if the control circuit is powered via the alternator, then there's a major problem if the belt snaps or if there's any other major fault which removes the alternator drag from the output shaft. But if that happens, all valves will automatically shut down and block the flow due to the lack of voltage to keep them open. The arrangement could be like this. The AC generator powers a power supply unit which powers the circuit. The circuit can sense magnets in a disc on the output shaft spinning past a sensor, a Hall effect sensor. The output from the circuit controls each of the 10 valves by either passing current through the coil around them or not passing current through the coil. And if they're all open, it's the same as there being completely free flow into the drum, and if they're all closed, you get no flow into the drum. some closed and some open, you get intermediate positions. You can use a disk to assess the rotation speed, but it's easier probably. It's not as significantly elegant as having a sensor. You can use the generated voltage by the AC generator to let your circuit sense if the generator has been spun at the right speed. You can do that quite readily if you wish. With that sort of arrangement, if the drive belt were to break or the alternator were to develop a serious fault, then the circuit voltage would drop off and the circuit would no longer supply current to the open valves, and all valves would close, shutting off the generator, which is exactly what's needed. Now all that's needed is a simple circuit to control the valves. Please understand clearly that I've never been trained in electronics, so I'm only self-taught, so feel completely free to consult an expert to provide you with a better circuit. The valve opens if fed 300 millimeters of current at 12 volts. That is 3.6 watts of power for each valve, or just 36 watts for all 10 valves. The alternator produces mains voltage, so we'll drop that down to around 12 volts, both for safety's sake and to make the circuit components cheaper. To drop the voltage down, we use a simple power supply comprising a 3 amp mains transformer here, which produces 12 volts on this side. The diode bridge here of 4 diodes is used to convert the output into pulsing DC, and a simple capacitor across the output smooths the power supply to a perfectly reasonable level. As with all circuits, and especially main circuits, we install a fuse or circuit breaker as the first component connected to the mains, and we insulate all metal components to make sure that we don't accidentally touch them and get a nasty shock. Once the voltage is down to 12 volts, the circuit's no more dangerous than a 12-volt car battery, and it's not necessary to insulate everything. The fuse is a 3 amp fuse. This circuit is deliberately not self-adjusting, as we want to use it to detect voltage differences coming in from the alternator, which is marked mains in this particular diagram. The most important thing is to detect a rise in voltage. That indicates that the generator is starting to rotate too fast, and so we want to switch off one or more valves. The circuit for each valve is the same as for all of the others, although the adjustment of each circuit is slightly different, so that the valves switch off at slightly different voltages. The switching circuit which we will use is called an operational amplifier, and thankfully that whole circuit comes ready-made in a standard chip. For example, the very cheap LM358 chip has got 2 separate operational amplifiers in it. This is the way that the 8-pin dual inline holding or chip itself has got the components inside it. You have the minus and plus inputs to the first operational amplifier there, and the output there, and the same for the second one. You've the power supply to the chip, plus over there and 0 over here. If we were to connect an LM358 into the circuit, we would connect it like that. Pins 8 and 4 connect to the LM358, which is then in business forever and ever and a day. If the voltage at pin 3 exceeds the voltage at pin 2, then the output on pin 1 will be high, which should be about 10 volts. Otherwise the voltage on pin 1 will be low, probably 1 volt or less. We will use the high voltage on pin 1 to switch on one of the valves, and we use a high power, high gain transistor like the TIP132 to do this. So the circuit that we're going to use is driven by the output on pin 1 of your LM358 chip. It has a current limiting resistor to power up the tip 132, which has a gain of at least 1000. We put a protection diode across the valve itself because it's a coil wound inside it, and we let the transistor drive the valve directly. The transistor is a very powerful and cheap transistor. Now that's the way that we connect the valve to the particular operational amplifier. The TIP132 can handle 100 volts and 8 amps and has a gain of at least 1000, often a lot more. So if it's passing 330 milliamps through the valve winding, then it will need a base current of 0.3 of 1 milliamp. That current flows through the resistor R, which has about 10 volts across it. Resistance equals volts over amps, or if you prefer, 10 volts divided by 0.0003 amps, which is 33,333 ohms, or 33k. However, we'll increase the base current by a factor of 3 and just use a 10k resistor. So this is our actual circuit here. The 10k resistor feeds TIP132 and powers the valve on and off, depending on which way the 358 op amp is actually operated. Now we need to get the LM358 to switch off, causing the voltage on pin 1 to drop low, starving the TIP of base current and cutting the power to the coil of the valve. And for that we need the voltage on pin 2 to rise above the voltage on pin 3. And we want that to happen if the power supply voltage rises. So if we connect a multi-turn 10k preset across the power supply, that looks like that or that. Those are two typical versions of it. Then the circuit becomes this. This allows us, by turning the screw on the preset resistor, we can set any voltage we like on the pin 2 connection of the operational amplifier. The last step is we want to provide a reference voltage which doesn't change if the power supply voltage increases. The approved way is to use a Zener diode with a resistor in series with it, and in theory the voltage drop across the Zener diode is a reliable reference voltage. I have not found that arrangement to work at all well, so I suggest using ordinary diodes such as the 1N5408 instead, using them like this. You put 4 of them in series and feed them with a 1K resistor, and that gives you a reference voltage caused by the voltage drop across each of these 4 diodes, and I have found that to be a reliable voltage source. Anyway, each to his own. So this gives about 10 milliamps flowing through the diode chain, and some 2.5 or 2 3/4 volts is generated across the diodes. That voltage does not alter appreciably if the power supply voltage increases. The second op amp in the LM5408 chip. What are we talking about? I'm sorry, that's wrong. The second op amp can be used to control the next valve. Pins 4 and 8 are also connected to the power lines, but what was pin 1 is now pin 7 for the second op amp. What was pin 2 is now pin 6, and what was pin 3 is now pin 5. The circuit is set up using a bench power supply. Measure the voltage of the power supply powered by the Donnie Watts alternator and then disconnect it. connect the bench supply in place of the alternator supply and set the voltage to exactly the same value. All op-amps are connected to the 4 diode reference voltage point. Let's say that we want the valves to drop out at every 5 volt increase of the mains voltage. If it is a 240 volt main supply, then the transformer drops that down to 12 volts, which makes the change 20 times smaller. So the power supply voltage will go up by only 5 divided by 20 volts, which is only 1/4 of 1 volt. So you adjust the bench power supply up by 1/4 of a volt and adjust the first variable resistor so that the first valve shuts off if the voltage rises by that 1/4 volt. Lowering the bench supply voltage by that 1/4 of a volt should have the valve clicking open again. This is repeated with all of the valves, so that the second valve drops shut at 1/2 volt higher voltage, the third valve drops closed at 3/4 of a volt increase over the original voltage, and so on. When you're starting the Donnie Watts generator, you need the valves open, so a 12 volt source has to be applied to the valves. Make sure that you do that through a press button switch and not a toggle switch, because you could easily forget to switch the toggle switch off after the system gets up to speed. So that's the Donnie Watts generator. It's easy to build if you're persistent. It's not difficult to control, and it is very effective and can power your entire house. All that's left in this document is the 2 patents, which are at the end of the document itself. This document is downloadable, so you can quite readily download it and take a look at it word by word. This is the original Donnie Watts diagram, with the exception that I put on the AA cross section here to show that these channel arms are actually triangular. They don't really need to be. That's by the way. You've got the cross section that he's drawn, and he's decided to put the generator directly in line with the output shaft and support it with a big angled support. The later design is very much more complicated, with moving parts and seals and a rotor whose weight is supported on a rotating axle, as well as rotating in the axle. The bearing itself has to supply a sideways thrust capable of supporting the weight of the rotor and water, and there's a movable jet which is suppressed by springs and pulled down by springs, but can be pushed upwards. There's also the possibility of a butterfly valve. There's also an air connection directly to outside air, and there is a spillway applied to the outer container. This is a very much more difficult arrangement, but anyway, the system itself is supposedly very technical. It shows us some interesting methods of alternating the rotor design. The important part here, which is physically difficult to make and to get balanced, is a spring-loaded pressure relief valve. This is the mechanical way of making sure that the generator doesn't run away with itself, because if it starts running away, the pressure inside increases and the valve is forced open and extra liquid squirts out in every direction all round, not adding to the drive of the drum at all. But that is the way that the design is organized. And he does say categorically that the areas of the jets must be at least should be not more than 1/8 of the area of the incoming supply pipe. That, of course, is not actually difficult to do. Thank you for listening.